Tests for outliers. We start by looking at table 13.3, and it has been remade to look better. What we have here is, if you go back quickly with this table, the first column is the name of the test. The second column, I should say the second and third column, they are subdivided. They show the situation as far as the knowledge of the population parameters are concerned. We can have the population mean known, and we may have the population mean unknown. When the population mean is unknown, we use we compute the sample mean and use the sample mean. We have now the situation as far as the variance is concerned. The variance may be known or not known. When the variance is not known, we will compute the variance from the sample. We have to realize that whenever we draw information from the sample, either computing the mean or computing the variance, or if we build a histogram, as we'll see in the fitness of good test, we lose degrees of freedom. Now, we have a column for the null hypothesis, and the null hypothesis is that our observations follow a normal distribution. The difference is how we evaluate normal distribution. If we know all population parameters, we use them. If we don't know any one of the population parameters or both of them, we use the sample to compute either the mean or the standard deviation. Then we have a column for the statistic. The statistic is the quantity to be tested. We will see that we reformulate the statistic. Well, we not reformulate the statistic. We reformulate the test itself, the statistical statement, to make it more intuitive. In other words, instead of testing a statistic that is computed by observation minus mean, population mean divided by standard deviation, we are going to test each individual observation directly. The PDF that we use is going to be when we know the variance, and this is very important. Okay, this is very important. When we know the variance, it is we have these situations 1 and 3 in red. We use a normal distribution. If we do not know the variance, we are going to use the t distribution or the tau distribution. Now, this is tricky at the beginning, but we have to if we have to keep that in mind. If the variance is derived from the same sample, from the same observations, we are going to use the tau distribution. If the the standard deviation S is derived or comes from independent sample, we use the t distribution. Okay, these may be tricky, but as a matter of fact, this is something that should be obvious in practice, in the sense that whether standard deviation has been computed from the sample that is being tested, or if it is being used from a different sample. Okay, for example, we may have be surveying in different days, and in the first day, with the same instrument, the first day we collect observations and compute lots of observations, compute the standard deviation from the sample. Okay, and then we use these standard deviation for all the remaining observations for day 1 and day 2. So which means that we are actually we have to use the student t distribution in the test for outliers, because we are testing samples that we are taking with independent sample that was observed in the beginning. And finally, we have the statistical statement, which we have testing if the observations lie within a certain threshold. So this is the left-hand side, and this is the right-hand side of the statistical distribution. So these would be here left, these would be right, and we are going to test every observation that lies in here. Well, actually the observation will be here. Every observation value that is here will be accepted with 1 minus alpha confidence level. Observations that lie at the outlying areas, it's going to be an outlier with so the observation will be rejected with a significance level alpha. Test for outliers. The situation 1 and 2, meaning population mean is known, we use the so-called expected residuals. The residuals are uncorrelated. Why they are uncorrelated? We're representing here for every observation I, we're going to have a residual, a uncorrelated residual that is going to be computed as the difference between the observation and the population mean. So it's uncorrelated because the observations are independent from the population. In situations 3 and 4, when the population mean is unknown, we are estimating the residuals from the sample. So what we have for every observation, the residual V estimated is going to be the difference between the observation and each observation I and the mean value of the observations. Okay, which means it's correlated then. It's the mean was derived from the observations that we are testing. The correlation factor is n minus 1 over n. Okay, which of course it is going to be it's going to get closer to becoming uncorrelated as we increase the number of observations. We can compute the statistical dependence of the observations. Okay, so and of course we can state then that the correlation between adjusted residuals they are due to the finiteness of the data set. Something that is very important also to realize is, well, there are two things here. The first one is what we mentioned about the situation 2 and 4 when the population variance or standard deviation is unknown. We use the sample standard deviation. Now, the sample standard deviation might have been derived independently from the sample that we are testing, or it might have been derived from the sample that we are testing. If it comes from an independent sample, we use the student's t distribution. If it comes from the tested sample, so from the observations that we are testing, we use the tau distribution. How do we compute this variance? Variance from the sample, we compute like this. This is the usual expression, n minus 1 summation of the square of the observations and their mean value. But if the population parameter is known, we should compute the standard deviation, okay, using the mean value, the population mean. So we have the same situation. Oh yeah, and there is another difference here because we are using the population mean. We divide it by n. Okay, because we are not losing any degree of freedom. We lose a degree of freedom in here, divided by n minus 1, because L bar is computed as a function of the observations. In this case here, what we have is Li are independent from the population. Now, I told you about the statistic. So by definition, the statistic in the test for outliers is given by the ratio between the difference between each observation and the population mean by the population standard deviation. If it's standardized, it is zero mean standard deviation. If we're dealing with the standardized normal distribution. Now, what happens then? And of course, we're going to have variations of this statistic for the situations when the mean is unknown or the population mean is unknown and the population standard deviation is unknown. So this is what we would be using, okay? So we'll be testing the statistic if the statistic y lies between these values minus psi and plus psi, okay? So the statistic is computed by this equation. It is nice and it is done, and I think you're going to see in most textbooks presented like that, but we prefer to rearrange that. We prefer to rearrange in such a way that we are testing directly each observations. We believe that this is actually more intuitive. So what we have then is, first of all, we replace the statistic. This is statistic y, and we now multiply each term by sigma, and then we add each term by mu. So this is what we could call the statistical statement that we make, and now we are testing if the observation itself lies within this interval. There is a concept of out of context and in context. Out of context, which is done in most times, and that's what we are going to focus, by the way. It's each observation is assessed individually to see whether the outlier is not too far from the other observations. Each observation is taken out of context and out of existence of other observations. No, I'm sorry. Each observation is taken out of context and the existence of the other observations is disregarded. The in context, all events are assessed as a unit. So all observations are looked at together and asked what observations should be removed. Each observation is taken in the context of there being a member of series. How do we do this out of context in context? So out of context is when we use the confidence level as we have defined. The in context will define a new confidence level, 1 minus A. So in such a way that the significance level A takes into account all tested elements. So what we going to have here is that 1 minus A will be less than 1 minus alpha. In other words, A is greater than alpha. So it is we can consider more rigorous testing. From this expression, we can make this development. We are going to arrive at the simple expression here that relates the significance level of the in context and the significance level of the out of context. It's what separates them, what relates them, is the number of observations or the number of degrees of freedom. Okay, so which means that if we're doing a in context test, but we want to use the same confidence level 1 minus alpha, we just basically replace alpha by this is going to be we use this relationship, and instead of using alpha here, we're going to use alpha divided by 2n, because we know that alpha is relates to n, to alpha, and a in alpha relates to n by n or by 1 over n. We are not going to use the in context, so we're going to focus on the out of context, on the mechanics of it. You are going to be using in context testing in certain situations in survey design, and mostly in precision survey applications. Here is how the PDF looks like. This is our usual 1 minus alpha confidence level. This is the out of context. In the in context, we have the situation now 1 minus A, and 1 minus A is less than 1 minus alpha. So there are some implications here in terms of type 1, type 2 error. Okay, this is alpha over 2. This is alpha over 2. This is a over 2. This is a over 2. So if you go back and look at this figure that we're showing now, okay, and in the under the light of type 1 and type 2 errors, you're going to see that these we're having now I mean, there are some implications in using out of context and in context testing. Test for outliers is an iterative operation, except when both population parameters are known. And this is the interesting thing. So what happens is that we have the largest outliers. They are removed first. When we remove the outliers and we evaluate sample mean and sample variance, they are now evaluated without the effect of the outliers, okay, which might create new outliers. So that's why I recommend this test to be an iterative operation. So what happens, the iterative process is as follows. Given a set of observations of n observations from I to n, we compute the mean standard deviation, okay, or we are given mean and standard deviation, one or the other. Again, we don't need to do iterative operation if we are using both population mean and variance. Okay, one of them have to be unknown. So the mean here in the standard deviation, one of them or both are coming from the sample. We test each observation. If we flag outliers, we remove that observation and we reevaluate either the mean or the standard deviation that comes from the sample. We repeat the test. If there are no outliers, we continue with our work. One important information, and I think this is very important, even though seldomly done in practice, that ideally we should investigate the source of error before rejecting an observation as an outlier. Because we remember that we discussed about the fact that observations should be honored. There is not such a thing as a wrong observation. And we also know that there are effects like systematic effects and blunders. So the idea is we should have an explanation for every single outlier. So we should have an evidence that would support the presence of a blunder or a systematic error, if that's the case. The other thing is that outliers we have Sometimes, that's a problem of not reading, just lecturing in real time. Sometimes the quantity being tested, okay, observations, we may use the same reasoning for residuals as well. We will see later on that we do that also. So the quantity that is tested may be a byproduct of a reduction process, okay, or has gone through a mathematical model, which means that the quantity may be, so if there is an imperfection, so the quantity may be flagged as outlier without really being an outlier. That's what I want to say. Okay, we may have a well, normal, healthy, a healthy observation, and suddenly it was flagged as outlier because after going through a reduction, an imperfect reduction process, and after going through an imperfect mathematical model, it became an outlier. So, which this is again things that we should keep in mind. I can tell you that in practice, people do the test for outliers, test on outliers, and whatever is flagged outlier will be removed, and the iteration should close fast. Maybe just one iteration would suffice most of the cases. Something I should have mentioned, if someone does iterations with test of outliers and it never converges, well, then the observations are all messed up. Probably there are heavy systematic error in the observations. So let's move along. Examples. Observation set. We are given 6 direction measurements. And the question is, are there outliers with respect to a calibration value that is given here? Okay, so 137, 41, 41.9, and the variance equals to 3.2. So in this case, we are given the population mean and population variance. So this came from a calibration value for the instrument we're using. So we take that as a representation of the population parameters. Significance level equals to 0.05, so 5%. So we are dealing with the situation when both alpha and mu, sorry, this is not alpha here, I apologize. This is sigma. So we're dealing with the population, with a situation when mu and sigma are given. So this here is a statistical statement. We know the value of the population mean. We know the value of the population standard deviation. We have to draw this value here from the normal distribution, standardized normal distribution with 1 minus alpha over 2 confidence level. Okay, why is alpha over 2? Again, remember, this is a two-tailed test. 1 minus alpha, alpha over 2, alpha over 2. Okay, so this side here corresponds to this limit. This side here corresponds to this limit. So in the solution, what we have, when you do the test, we're going to see that observation P0 or L6, P6 or L6 is an outlier. Okay? There is no need for iteration. Why? Why is that? Sample mean after the outlier removed equals to this is just the value in seconds, 41.4 seconds, and the variance, sample variance, oh, by the way, I'm sorry, this is variance. Variance is 3.1. Standard deviation, 1.7. Okay? Let's look how we got this value for psi sub n 0, 1, 1 minus alpha over 2. Standardized normal distribution. Okay? So what was the alpha? Alpha was 0.05, right? And the value that we're going to get, okay, alpha equals to 0.05. Alpha over 2 equals to 0.025. 1 minus alpha over 2 equals to 0.975, right? 5 times 5 is 10, 8, 12, yes. So this is the value that we want to get. This is a probability. So what we are doing here, we're doing the inverse operation as we did the first time we look at the standardized normal distribution table. We want to determine the value, the abscissa value, okay? We want to determine the value here, psi, okay? So we know the this is 1 minus alpha over 2, oops, 1.906, okay? So the value psi, our psi is 1.96 for a confidence level here of 97.5%. Okay, so that's how we evaluated psi. Here we go, 1.96. Another example, same observation set. Now we are going to do the test using sample mean and sample variance. Okay, so which means we have to compute that. So now we're using this statistical statement here. We have each observation tested to see if it lies between the mean value plus this coefficient here that accounts for the correlation. Remember that when we derive the values from the sample, we are creating correlation. Here we have the standard deviation, sample standard deviation, and here we have now the cutoff value that we draw from the tau distribution with n minus 1 degrees of freedom, 1 minus alpha over 2 confidence level. So we are basically adding plus and minus. So we're adding this thing here. Okay, so in some sense, what we have is this thing here. We have the mean value, okay, and we have our cutoff from the mean value, which is n minus 1 over n plus square root s, the value that we draw from the statistical table, minus n minus 1 n square root s, the same value. So the difference here is the negative sign, and of course observations. The observations that fall inside this area will be accepted with 1 minus alpha confidence level. Okay, and the other ones will be rejected. Let's use alpha equals to 0.05, so 5%. From the table we get 1.814. We're going to look at how we got that. For the first iteration, these are the values that we used. Mean value is 37.3. Standard deviation 10.1. When we apply the test, we are going to see that L6 is an outlier. Okay, so L6 is 42, 54, 20, 42, 16. So L6 will be around here somewhere. All the other observations will be here. L1, L2, L3, L4, L5, all falling here. Then we remove the outlier. We compute a new value for mean, new value for the variance. We then perform the second iteration, no outlier. So here we have then the final mean, final variance, standard deviation. Tau distribution. So again, we know that we're dealing with 0.975. Okay, how many degrees of freedom we have? We have 6 observations, n equals to 6, but we lose 1 degree of freedom. We are drawing the quantities from the sample, so we're losing 1 degree of freedom. So our degrees of freedom, ni, is going to be n minus 1 equals to 5. Okay, we know that this is 1 minus alpha over 2 as we used before. So what we have then is, here we go. This is the value, our cutoff value. This is the tau distribution. Here is the cutoff value. Okay, so this is it. I finished the slide too suddenly. This is it about the test on outliers. Okay, and we have, yeah, that's lengthy. I'll have to cut these in two. I'll use 2 videos for that. Or maybe not. Maybe I can. No, okay. Yeah, I'll do something. I'll do something on that. Thank you, guys. See you later.